117,000 years ago, a river flooded a terrace on Java. It swept bones together and buried them in sand. Among them were 12 human skullcaps. They belonged to Homo erectus, the youngest securely dated occurrence of that name anywhere on Earth. At the other end, fossils with clear Homo erectus affinities appear close to 2 million years ago. If success means persistence through time and spread across landscapes, no other known human species has yet matched that record. The evidence points not to one superpower, but to a portfolio. Different populations combine mobility, local knowledge, varied technologies, and socially learned behavior. Not a huge brain, not the handaxe, not fire, not even the famous running body. Ngandong carries the warning hidden inside the title. A lineage can be extraordinarily successful and still disappear. Most successful is a dangerous phrase in evolution. Nature does not award medals. A lineage that lasts longer is not morally better, more intelligent, or destined to win. Extinction is not a verdict on worth. So this film will use only two measurements that the fossil record can actually approach: duration and geographic reach. Even those measurements come with a problem. The label Homo erectus covers fossils separated by enormous distances and almost 2 million years. Some researchers place the earlier African fossils in a separate species, Homo ergaster. The small-bodied hominins from Dmanisi in Georgia have also received other names. Asian populations developed their own regional anatomy. The borders between these groups remain debated. Here, Homo erectus sensu lato, Homo erectus in the broad sense, is an operational umbrella. It does not mean that one uniform population marched across the old world, unchanged from beginning to end. It means that a recognizable family of populations shared enough anatomy and evolutionary history for many researchers to discuss them together while disagreeing about where one species stops and another begins. That boundary matters because the old story begins with a clean transformation. A small, primitive ancestor supposedly becomes taller, smarter, and technologically advanced. The new human then leaves Africa and dominates the Pleistocene. The fossils do not arrange themselves so neatly. At Trinil in South Africa, a partial cranium called DNH 134 has clear Homo erectus affinities and dates to roughly 2 million years ago. Yet it lived in a landscape that also held Australopithecus and Paranthropus. In East Turkana, an occipital bone called KNM 2598 is older than 1.855 million years, but the beginning of the lineage remains represented by fragments. At Gona in Ethiopia, the reconstructed DN5 cranium, about 1.6 to 1.5 million years old, combines an erectus-like brain case with a small brain and more ancestral features in the face and teeth. This is not a creature appearing fully assembled. It is a mosaic emerging inside a crowded human world. The timing reinforces that point. Early Homo fossils with different combinations of brain size, face shape, teeth, and body form overlap, rather than lining up like frames in a transformation. Some populations retained ancestral features after more classically erectus anatomy already existed elsewhere. Even the distinction between early Homo and early Homo erectus becomes blurred in specimens such as DN5 and the Dmanisi skulls. That means longevity cannot be credited to one sudden upgrade. The long record, instead, contains populations changing at different rates, in different places, while other human lineages remained beside them. The beginning looks less like a new model replacing an old one, and more like several experiments running at once. That mosaic gives us the first clue to its endurance. Variation was not a late imperfection added to a perfect design. Variation was present near the beginning. The most famous Homo erectus body belongs to an adolescent found near Nariokotom, west of Lake Turkana. His skeleton preserves long legs and human-like body proportions. He is often made to stand for the entire species, tall, narrow, almost modern from the neck down. But Dmanisi refuses that portrait. The individuals there were smaller. Their shoulders and arms retained primitive features. Their bodies were not miniature versions of ours, yet their limb proportions and lower limb anatomy still indicate the capability for long-distance terrestrial travel. That combination is more revealing than a single ideal skeleton. Efficient movement did not require every part of the body to become modern at once. A population could remain small-brained and anatomically mixed while becoming increasingly committed to life on the ground. Near Ileret in Kenya, mud preserved a more direct trace. Researchers documented 97 hominin footprints across several surfaces dating to about 1.5 million years ago. Most, perhaps all, were probably made by Homo erectus, although other hominins lived in the region and the attribution is not absolute. The best preserved tracks record a pattern of external foot motion statistically similar to that of modern humans. The heel receives the step. Weight passes forward. The foot stiffens into a lever for toe-off. Bone had suggested a traveling body. Here, the ground records that body in motion. The footprints also protect us from another exaggeration. They occur on several surfaces, not one frozen migration scene. Different individuals passed through lakeshore mud at different moments. The trace is powerful because it is ordinary, repeated steps at a resource-rich margin. It shows locomotion as daily ecology rather than a single march out of Africa. This matters because terrestrial mobility changes the scale at which an animal can solve problems. A more efficient walker can connect water, stone, carcasses, plant foods, and shelter across a wider area. It can leave a depleted patch and reach another. It can carry tools or food without giving up the hands needed to do so. Distance becomes usable space. Then comes the famous leap. If Homo erectus could travel efficiently, perhaps it ran prey to exhaustion beneath the midday sun. The endurance running hypothesis is serious. Human bodies possess a suite of features useful in distance running, and researchers have argued that several became important around the origin of Homo. A stabilized head, spring-like structures in the legs and feet, and the ability to shed heat while moving could make sustained running possible. Possible is not the same as demonstrated. No fossil preserves a persistence hunt. Anatomy rarely has only one function. Long legs also make walking cheaper. Features that help stabilize a runner can assist balance in other movements. Critics have questioned whether the archaeological record and recent hunter-gatherer comparisons support endurance. Running as a major, early hunting strategy. We also cannot inspect fossil skin and confidently count sweat glands. We do not know the exact distribution of body hair in Homo erectus. The old image of a completely hairless runner following one antelope for hours is a reconstruction built from hypotheses, not a scene recovered from the ground. Homo erectus may have run. Some populations may have used persistence tactics. But the title cannot rest on that story. The stronger conclusion is simpler. These bodies enlarged the radius of everyday life. They made repeated terrestrial movement less costly. That capacity could support hunting, scavenging, gathering, transporting, and dispersal without requiring one universal behavior. Mobility was the first component of the portfolio. It was not a destination. It was the ability to encounter more options. At Dmanisi, the expected equipment is missing. The site lies in the southern Caucasus, between two rivers. Nearly 1.8 million years ago, this was not a heroic outpost occupied by one named expedition. Stratified stone artifacts show repeated use of the area between about 1.85 and 1.78 million years ago, possibly across 80,000 years. The fossils accumulated later within that sequence. Repeated occupation changes the meaning of dispersal. We are not watching one group decide to leave a continent. The record does not preserve a map, a destination, or a motive. It records populations returning to, or remaining within, a region beyond Africa across many generations. What those populations carried is as important as what they did not. Their brains were small. Their skulls retained ancestral features. Endocasts, the impressions left by brains against the inside of the skull, indicate that early Homo at Dmanisi still had a primitive organization in parts of frontal region. More modern human-like organization appears later in African Homo erectus. This does not tell us that the Dmanisi hominins were unintelligent. An endocast is not a thought, and brain shape is not an intelligence score. It tells us something more precise. Early expansion into Eurasia did not wait for a brain organized like ours. The tools make the contradiction sharper. Dmanisi preserves simple cores and flakes. They could produce cutting edges, but they are not the large, carefully shaped bifaces that later became an icon of Homo erectus. The earliest known Acheulean artifacts at Kokiseli in Kenya date to about 1.76 million years ago, close to the Dmanisi sequence, but on the other side of the dispersal. The handaxe was not the passport that first opened Eurasia. Fire cannot serve as that passport either. Evidence for early fire has become older and stronger, but no securely documented, lineage-wide fire system stands before Dmanisi and explains the journey. Nor do we need to imagine one. Animals expand their ranges without knowing they have crossed a continental boundary. Populations follow connected habitats, water, food, and terrain. Across generations, a range can grow without a single migration plan. We do not know the route taken by the Dmanisi population or the exact pressures behind it. Calling them explorers would import a modern intention. Saying they merely followed herds would pretend one food source explains their ecology. What Dmanisi proves is narrower and more disruptive. Small-bodied, small-brained early humans using core and flake technology repeatedly occupied temperate Eurasia. 3 popular prerequisites: large brains, modern-like frontal organization, and Acheulean handaxes arrived too late to explain that fact. So the second element of the portfolio was not advanced equipment. It was the ability to operate before one perfect package existed. The Acheulean handaxe remains one of the most compelling objects in prehistory. A suitable stone is struck from two faces. Each removal changes the angles available for the next. The maker must manage fracture, preserve a usable edge, and continue through a sequence that can fail with one misplaced blow. At Kokisele, artifacts with this new bifacial strategy appear around 1.76 million years ago. But the same site complex also contains Oldowan technology. One did not immediately erase the other. At Gona in Ethiopia, the pattern becomes personal. Two Homo erectus crania, different in size and separated in age, occur with both Mode 1 core and flake tools and Mode 2 Acheulean artifacts. The association does not identify the hand that made each stone. It does show that one species name cannot be assigned one unchanging toolkit. The two skulls also resist a simple brain and technology equation. One is small and lightly built, the other is larger and more robust. Both belong within the variation assigned to Homo erectus, and both occur in archaeological contexts containing more than one technological strategy. Neither brain size nor tool category sorts the record into a clean hierarchy. Calling Mode 1 primitive and Mode 2 advanced hides the decision that matters. A simple flake can be produced quickly and gives an extremely sharp edge. A bifest demands more material, time, and control, but may be maintainable and useful in other ways. Different tasks, raw materials, and movement patterns can reward different solutions. Technological flexibility is not a ladder. It is the ability to choose how much effort a problem deserves. We should be equally careful with the handaxe itself. Its shape records a controlled manufacturing sequence. It does not reveal one universal purpose. It cannot tell us that every maker saw a perfect template hidden inside the stone. It does not prove spoken instruction. And the survival of bifacial traditions across deep time does not mean that 1,000,000 years passed without change. The category, Acheulean, contains variation in raw materials, blank selection, shaping, and regional history. Some Asian assemblages contain bifaces, others do not. Some Homo erectus populations continued to use core and flake methods. Long duration can preserve diversity as easily as uniformity. On Java, another material widens the picture. In the old Dubois collection from Trinil, researchers examined freshwater mussel shells recovered from the Homo erectus type locality. Several shells had been opened by piercing the area where the closing mussel attached. One shell had a sharpened edge used as a tool. Another carried a geometric zigzag engraved deliberately into its surface. Sediment inside the shells placed the assemblage broadly between about 500,000 and 400,000 years ago. The incision is controlled. Its meaning is not. We cannot call it art. We cannot call it writing, ritual, or a symbol. The original study explicitly states that its function and meaning cannot currently be assessed. What the object does show is that an Asian Homo erectus population engaged with a river resource in several ways: as food, as a tool material, and as a surface that could be marked with deliberate precision. That is a richer technological image than the solitary handaxe. The portfolio now has a second component. Mobility increased the number of situations a population could meet. technological diversity increased the number of responses available inside those situations. A quick flake, a shaped biface, and a sharpened shell are not stages in one inevitable ascent. They are different negotiations with material. But one material has been made to explain almost everything: fire. Deep inside Wonderwerk Cave in South Africa, roughly 30 meters from the present entrance, researchers found burned bone and ash within early Pleistocene deposits. A 2012 study established in situ burning around 1 million years ago. In 2026, a new analysis pushed the story deeper. The researchers tested small mammal bones from 2 strata using 2 independent approaches. Fourier transform infrared spectroscopy detects changes caused by high heat. A new luminescence method distinguishes heated fossil bone by the way it responds to light. The 2 methods converge. Burning was not spread uniformly. It clustered in discrete areas, and its pattern recurred in layers, separated in the cave sequence. For the older stratum, the current age constraint is broad, between 1.79 and 1.07 million years. That range prevents a dramatic exact date. Yet the location and spatial pattern make repeated natural grass fires deep inside the cave an implausible explanation. Early hominins brought fire inward on more than one occasion. The authors consider Homo erectus the most likely user, but Wonderwerk has no diagnostic hominin fossil in these layers. The evidence belongs first to early Acheulean hominins, not automatically to every population called Homo erectus. It also does not show fire production. No one at Wonderwerk is preserved striking sparks or drilling wood. There is no demonstrated cooking scene. The deposits do not grant us a ring of people exchanging stories around a permanent hearth. Early groups may have collected natural fire, transported it, and maintained it. They may have used it intermittently long before the practice became common across many sites. Wonderwerk now makes very early engagement with fire harder to dismiss, while leaving the exact technique unresolved. That combination, strong trace, limited interpretation, is precisely why the site matters. Fire could change risk after dark. It could alter materials, warmth, light, and food. But one early site cannot explain the whole geographic and temporal span. Dmanisi shows that expansion did not wait for securely documented habitual fire. Wonderwerk shows that at least some early populations added fire to their options remarkably early. The difference is the thesis. Fire was not the single switch that turned an animal into a successful human. It was another powerful element that populations could acquire, lose, maintain, or use differently. Crusts can create an illusion. Mark Africa, the Caucasus, China, and Java, then color everything between them, and Homo erectus appears to have mastered every environment across the Old World. Fossils do not prove continuous occupation of that colored space. Nor does presence in several regions mean one body could tolerate every habitat without changing behavior. Ecological flexibility has to be demonstrated at the scale where choices meet resources. Engaji Nanyori in Tanzania provides that scale. Around 1 million years ago, the landscape near this part of Oldupai Gorge was severely arid. Pollen, sediments, plant remains, fauna, climate models, and geological chemistry converge on semi-desert conditions. Vegetation cover was reduced. Water and food were not evenly distributed. The archaeological pattern is not one of wandering everywhere. It is one of repeated focality. Hominins returned to fluvial zones, where channels and confluences concentrated fresh water, stone, plants, and animals. Tools and butchered fauna occur around these ecological nodes across long intervals. That conclusion does not come from a desert-looking backdrop. It comes from several records that agree. Pollen from drought-adapted plants, sediment chemistry, evidence of landscape burning, animal communities, dated deposits, and regional climate and vegetation modeling. Archaeology is meaningful here because it sits inside a measured local environment. The site connects a behavior to the pressure it was answering. This was not freedom from environmental limits. It was a way of using the limits. When a landscape becomes drier, the value of water points rises. Resources become concentrated, but so do competition and risk. A reliable node reduces search cost. Dependence on it also makes its failure more dangerous. Flexibility contains trade-offs. The evidence does not tell us that people stored water, mapped a territory, or planned a seasonal schedule. It does show recurrent use of the same kind of high-value place under extreme conditions. The behavior was spatially focused, not ecologically limitless. Now compare that with Trinil. There, riverine shellfish and shell material entered the behavioral repertoire of an Asian population. At Dmanisi, simple stone tools supported repeated occupation in a temperate region. At Wonderwerk, fire was brought into a deep cave. These are not copies of one African survival kit. They are local combinations. This is what ecological flexibility means in the strongest version the evidence allows. It is not the ability to remain unchanged while the world changes around you. It is the capacity to alter which places, materials, and behaviors carry the load. Mobility brings a population into contact with new opportunities. Technology converts some opportunities into food, cutting edges, or controlled heat. Repeated land use turns scattered resources into a workable geography. Each component increases the value of the others. That feedback loop is more powerful than a single superpower, because it can produce more than one workable answer. But a behavioral portfolio exists only for as long as information survives. A skilled action that dies with one individual is not yet a durable adaptation. Stone does not preserve a lesson. It preserves the result of one. Producing a sharp flake is not random impact. The maker must select a platform, control the angle of a blow, and recognize which surfaces can release the next flake. Shaping a bifes extends that sequence. These skills require practice, and their recurrence across generations strongly implies social learning. The exact channel remains invisible. In a modern experiment, researchers ask adult participants to transmit Oldowan napping skills along chains. Some could only inspect finished tools. Others watched a demonstration, received gestures, active teaching, or spoken instruction. Teaching improved transmission, and language improved it further under the conditions of the experiment. That result shows why communication can matter in a difficult manual skill. It does not transport modern speech back 2 million years. The participants were Homo sapiens. Their learning periods were brief. Fossil hominins may have watched for years, practiced beside experienced makers, copied outcomes, followed gestures, received correction, or used forms of vocal communication that left no trace. We can say that information moved. We cannot hear how. At Ileret, the footprints add a minimal physical fact. Across multiple surfaces near the ancient lakeshore, at least 20 individuals left tracks. The surfaces do not preserve one crowd walking together. They do show repeated use of the same resource zone by multiple hominins, most plausibly Homo erectus. Shared habitat creates the opportunity for observation. It does not reveal a family, a hunting party, or a division of labor. Those would be stories added to the tracks. Dmanisi offers an even more emotionally charged trace. One adult, represented by skull D3444 and mandible D3900, had lost all but one tooth well before death. The jawbone remodeled after the teeth disappeared, showing that the individual survived for a substantial period with severe chewing limitations. This fossil is often introduced as the earliest proof of compassion. A group, we are told, must have softened food, chewed it for the individual, or carried a dependent elder. Any of those actions is possible. None is preserved. Soft plant foods, marrow, brains, small pieces of animal tissue, and other resources may have reduced the need for full chewing. More importantly, a wild bonobo skull with extensive tooth loss provides a direct warning. Survival without most teeth can occur in another primate without demonstrating a human system of food preparation or care. The bonobo does not prove that the Dmanisi individual lived alone. It proves that tooth loss has more than one possible explanation. That may feel like losing the most human part of the story. In fact, it gives us a more defensible one. Homo erectus populations were not successful because one fossil lets us assign them our preferred virtue. They were successful because workable behavior could persist among individuals who occupied the same places, handled the same materials, and reproduced difficult procedures across time. Some communities may have supported impaired members. The fossil record cannot tell us how often, by what means, or with what intention. The human payoff lies in the dependency of the portfolio itself. Longlegs belong to individuals. A technological tradition does not. Fire maintenance, napping procedures, resource locations, and the timing of returns become more reliable when information survives its first user. Mobility encounters options. Local behavior tests them. Social learning preserves enough of what works for another generation to begin, without starting from zero. This is not proof of modern culture. It is the minimum social architecture required for durable flexibility. Return to the Solo River on Java. At Ngandong, the 12 skullcaps and 2 lower leg bones were not found in a camp or grave. They came from a bone bed assembled by a powerful flood. The river moved and mixed remains before sediment sealed them. Multiple dating methods place the deposit between 117,000 and 108,000 years ago. These are the youngest securely dated fossils assigned to Homo erectus, are not necessarily the last individuals who lived. A last occurrence in the known record is not the same as the moment a lineage became extinct. We also do not know what ended it. Southeast Asian environments were changing. Forests expanded in parts of the region, and the open habitats associated with some Homo erectus records contracted. That shift may have narrowed suitable range, but the timing is not synchronized tightly enough to declare rainforest the killer. The Ngandong deposit does not preserve a collision with Homo sapiens. It does not record Denisovans arriving, a volcano striking, or one isolated group watching its final fire die. Those are endings written by our appetite for a scene. The real ending was probably distributed. Populations disappeared at different times in different regions. Some may have been replaced. Some may have mixed with other humans. Some may have lost the demographic margin needed to recover from local shocks. The evidence cannot yet assign their relative weight. Extinctions, therefore, does not reverse the answer to the title. By the operational measures used here, Homo erectus sensu lato remains an extraordinary human success, a fossil span of roughly 1.9 million years, and a distribution reaching from Africa through parts of Eurasia to island, Southeast Asia. The broad label is doing real work in that sentence. If future research divides these fossils into several species, the duration assigned to any one name may shrink. If it joins more populations together, the span may grow. That is why this film does not claim an eternal record. It claims that, under a declared and widely used broad classification, the combination of time and range is exceptional. The title is a testable interpretation, not a law of evolution. That success did not come from being perfectly adapted. Perfect adaptation is fragile because environments move. It did not come from one body. Tall Nariocotum-like forms existed alongside smaller, more primitive mosaics. It did not come from one brain threshold. Dmanisi was occupied before modern-like frontal organization appeared. It did not come from one tool. Core and flake strategies overlapped with bifaces, and shell entered the repertoire on Java. It did not come from one command of fire. Wonderwerk reveals early repeated use while leaving production, frequency, and taxon uncertain. The best supported answer is a feedback loop. Terrestrial efficiency widened the field of possible resources. Flexible behavior turned local stone, shell, water, animals, and sometimes fire into different solutions. Social learning allowed at least some procedures to outlast their makers. Across the record, variation among populations means no single narrow formula can explain the whole span. That model cannot be proven like an experiment. No 2 million year control group exists, but it explains more of the dated record with fewer invented prerequisites than the stories built around running, handaxes, fire, or brain size alone. And, in 2026, 6 teeth from China added an unexpected afterimage. Researchers recovered ancient enamel proteins from Homo erectus specimens around 400,000 years old at Zhoukoudian, Hexian, and Sunjadong. All 6 shared 2 amino acid variants. One has not been identified in the other sampled human lineages. Another also occurs in Denisovans. That shared variant makes East Asian Homo erectus a candidate source for a much older genetic contribution previously inferred in a Denisovan genome. Candidate is the essential word. These proteins are not a complete Homo erectus genome. They do not prove a particular mating event, and they do not show direct Homo erectus ancestry in people alive today. They do show that completely gone may be too simple. A lineage can vanish as a recognizable population, while fragments of its history pass through another human lineage. The flood at Ngandong preserved no final speech and no final stand. It preserved bones stripped of biography. Yet, those bones now mean something different from the opening. They are not evidence that a fossil record lasting almost 2 million years should be read as failure. They are evidence that success was never immortality. For almost 2 million years, populations within the broad Homo erectus lineage kept finding another workable combination. Not one perfect body, not one perfect tool, not one perfect world. Another route, another material, another place where water gathered. Another skill carried long enough for someone else to learn it. That is why Earth's most successful human was not us. Not yet.